Good afternoon, everyone. I hope you all enjoyed your lunch. My name is James Allardice. I'm the co-founder of Orange Jellyfish, a software consultancy based in London. I'd like to say a quick thank you to the DevConf organisers for inviting me to speak here today, and of course to all of you for attending this session. Some of you might have picked up on the fact that the title of this talk is based on the infamously catchy song from the Disney movie Frozen. I had wanted to expand that theme throughout the slides, but unfortunately it's difficult to associate a film about singing snowmen and reindeer with blockchains, so I had to let it go. This talk was originally designed as a workshop where everyone joins in and we all build a blockchain network together, and by the end everyone's mining a cryptocurrency between themselves. Unfortunately, we're not going to have time for that today in this session, so I'll be doing a lot of the coding myself. Live coding in a conference, nothing ever goes wrong with that. However, if you would like to follow along, or later on after the session, you can clone the repository here, and you can reset to the beginning of the session, effectively where we are right now, by checking out this boilerplate tag. We're going to be using JavaScript in this session, which is probably not a language that you'd usually want to use building a blockchain for a production purpose, but it's great for quick examples and prototyping, so it's quite well suited for this kind of thing. So we're starting with some boilerplate setup, which gives us an HTTP server using a module from the Node.js package manager npm, which many of you have probably heard of and used, and that module is called Express. And we've also got a peer-to-peer connection configured via a module called Discovery Swarm. Having that all set up allows us to kind of just focus on the interesting bits during this session. So I'll be jumping between some code and the slides throughout. So we've already got a bit of code. I won't go into details now. The useful blockchain-related stuff we'll fill in as we go. So let's get started. A blockchain is, unsurprisingly, a chain made up of blocks. This is a terrible picture, really, because it's not really a chain, but you get the idea. So what is a block? We can think of it as a container for some data, like a block of data. And one of the first pieces of data that we'll encapsulate in our block is an index, just an incrementing number, digit. This is used so that we can easily keep track of how long our chain is as it grows. We'll also include a timestamp so that there's a record of when each block was created, and some arbitrary data. The index and the timestamp were metadata related to the creation of the block. But the data attribute is where we can put something more interesting, the stuff that we actually want to store on our blockchain. Depending on the functionality of our blockchain or the idea behind it, there's likely to be some strict rules around the value of that attribute. It could, for example, encode a transaction between two parties in a very specific format, if our blockchain was to back a cryptocurrency. And we'll look more into that shortly. So these three attributes give us a nice foundation for our block. It almost seems like something that could be used as a classic example when teaching object-oriented programming. So let's put that down in some JavaScript code. So we'll start by defining a class for our block. We're using ES6 compiled with Babel, which allows us to write modern JavaScript. that still runs everywhere. And our block is going to expect the index that we saw earlier, the data, which we'll assume is some JSON, and we'll convert it into a string here, and the timestamp, which we can create when our block is instantiated. Cool. We're still missing some important attributes, though. We need to add a hash of the data to our block. And we'll take a quick detour to look at what that actually means. So a hash algorithm is a mathematical function. The output of a hash algorithm is a hash value, sometimes called a digest. One of the key attributes of a hash function is that no matter the length of the input, the digest is always of a fixed length. So in the SHA-256 algorithm, which is that used by Bitcoin and many other blockchain implementations, the output in hexadecimal form is always 64 characters long. Another key attribute of hash functions is that even minor changes to the input, such as this change from a lowercase f to an uppercase f, result in significant changes to the output. So you can see that the hash values, digests, in all three cases here are completely and utterly different from each other. And the final important feature is that hash functions are one-way, which means it's very easy, very cheap in computing power terms, to compute a digest for any given value, but it's incredibly difficult, or impossible even, given current computing power, to do the reverse, to take a digest and determine what the original value that produced it was. So we can extend our block class to include a method for creating a hash of the block. We can use the built-in Node.js crypto module to create a SHA-256 hash, to update that hash with the data in our block, which we can just concatenate together. And we can return a digest in hexadecimal form. So for the first block in the chain, this would pretty much be enough. But there's something very important still missing. Currently, aside from the index, there's no way to link these blocks together into a chain. So we'll introduce another property to the block. We'll add in the hash of the previous block. And this is what allows us to actually form a chain. So in my little diagram here, you can see that the previous hash on the right-hand block corresponds to the hash of the left-hand block. And there's another very important piece of this puzzle, which is where the integrity of a blockchain comes from. So if you recall that hashing method that we just added to the block class, you'll remember that we produced the digest from a concatenation of the block data and the metadata. So that was the data, the index, and the timestamp. So before we look at the solution to that, let's have a think about the problem as things currently stand. Consider the following chain. So the data in this chain, the top row in black, encodes transactions between users. We can see that every block has some data, a hash, and the bottom row is the previous hash. If a malicious actor, someone has come along and has been able to modify one of these blocks, so Eve has managed to come and change the transaction represented by the first block to pay her rather than Bob. Because the data of the block has changed, the hash will change too. If you remember, small changes to input result in large changes to the hash, so the contents of the transaction has changed slightly, but the hash will have to be recalculated, otherwise the block will be invalid. And in turn, the following block needs to be modified because it has a reference to the previous hash, which has now changed. But as things currently stand, that's all that would have to change. The digest of the second block, again made up of just the data, the index, and the timestamp, will still be valid in this case. The data of this block hasn't changed, its index hasn't changed, its own hash therefore hasn't changed, just its reference to the previous block has changed. So in this scenario, an attacker has been able to quite straightforwardly modify a historical transaction to redirect money effectively to themselves without much difficulty. So we need to update the digest of each block to include that of the previous block. And we can do that by extending the create hash method to include that previous hash reference. So now, if a malicious actor was able to change a historical block, the block, when it creates our hash here, because it includes the previous hash, which is now changed, this block would become invalid, and therefore the next block would become invalid, and so on, all the way up the chain. So let's say that the data for each of our blocks should be a single transaction object, which we can model once again with a class. A transaction needs a few properties, such as who is sending money, who they're sending it to, and how much. And that's about all we need for a basic transaction that kind of represents those we saw in the example a minute ago. So now that we have the ability to create transaction objects and block objects, we need to manually create the first block in the chain to kick things off. The first block is usually known as the Genesis block. And to create the Genesis block, we're going to need another new class, this time to represent our blockchain itself. So we'll call it blockchain. And we'll set up a chain of blocks as an array. And then we'll create a Genesis block. So the Genesis block is made up of a transaction for the data. So we're going to say that all of our blocks contain a single transaction. In reality, blocks would contain many, but for the purposes of this demo, we'll just say a block contains a single transaction. And that transaction is going to send money from nowhere to some address, which we'll use Alice again. And we'll need a block with an index of 0, as it's the first block in the chain. The data of that block is the transaction. And the previous hash, since we don't have a previous block, we can just create a fake hash of 64 zeros. And we can add that Genesis block to our chain, to our array. Just import the other modules. Okay. So we'll also need a method to generate the next block in the chain. So we have one. It contains effectively a fairly useless transaction and a fake previous hash because we don't have a previous block. So we'll add another method here, create block, which takes some data, again, another transaction. And we'll add that to our chain. We'll use some of the information from our existing previous block, the Genesis block, to work out some of the properties of our new block. So, for example, the index is the index of the previous block plus 1. So we can instantiate a new block using that new index, the data that's been provided, and the hash of the previous block to keep forming that chain. And we can add that new block to the chain as well. And after that, one more function to validate a block. So these will all become very important shortly when we start interacting with the chain. So given a block, say from some other arbitrary client in this network, we need a way to determine whether it's actually valid. And this is going to be very, very naive implementation for sake of time. But given any new block, we can assert that the new block references our latest block via its hash and its index. So if that condition holds true, we can be fairly certain that that block is valid for our chain because its hash, its previous hash, matches our current latest hash, and its index directly follows on from our latest index. So following all that, we're able to now get our node, when it starts up, to create a new chain. Like so. So at this point, we have a pretty good functional blockchain made up of validated blocks representing individual transactions. We can't yet really control our blockchain at all. So we're going to add a very limited HTTP interface. We've already got a server set up so that we can issue some commands to our node and start making use of it. So the first thing we'll add is an HTTP route handler for a GET request to /blockchain. And we can use this to simply return the current state of our chain so that we can see what it looks like. I called it chain there and not there. And another route, and we'll run through an example of these in a second, to handle a HTTP post request to actually create a new block in our chain. We'll put a bit of output here so we can see it happening. And we can now instruct our chain to create a block with a new transaction in it using the data from the post request. And we can then just respond over HTTP to the client, just with a 201 to say that that block has been created. I'll need to import the transaction class. So, having done that, we should now be able to interact with our running node. I'll zoom in a bit on that pane. So it's set up to pick a random free port and start the HTTP server on there. So if I now curl that port and hit that blockchain route, we get some JSON back showing the current state of our chain, which we can see contains one single block. It's not formatted particularly well down in that bottom corner, but it contains one block with our initial Genesis transaction with the fake previous hash and its own actual hash. We can also create a block by posting some data to the block endpoint. We see in the pane above, we've hit that output line, so we've created a new block. And if we were to request the full chain again, we can see it now contains our new block, which we encoded within a transaction from X to Y for an amount of 100. And you can see that the previous hash of that second block matches the hash of the first block. So we can see that what we're doing is kind of working. We're getting a chain of hash to a previous hash. That was an example of the request I used to create that new block. There's one more key problem, though, which you might have heard referred to as the double spend problem. And the issue is that we could currently create a block and broadcast it out to a network containing a transaction intended to send money to some other person. We could then broadcast another block containing a different transaction, spending effectively the same money, but sending it to someone else. And if that second transaction was picked up by the network and treated as a valid block, the first recipient would effectively, or could effectively in some scenarios, see their their money, their transaction, overwritten by the replacement because we've submitted 2 blocks at the same index, but individual nodes in the network will have picked up 1 block and run with that, and the other will get dropped as one chain grows longer. So the solution to this problem was the key innovation in the original Bitcoin white paper, and it's known as proof of work. So the solution starts with our same example from earlier, when we looked at the digest of the string A. So the digest on the right here doesn't look very special. There's nothing notable about it. So recall that one of the properties of hashes is that very small changes lead to very large changes in the output. And the proof of work algorithm used by Bitcoin and many other blockchain implementations use this property. So when creating a new block, rather than just hashing the data and accepting the digest as it is, we need to obtain a digest that satisfies some criteria. Let's say that we require the hash to start with 5 zeros. You can see here that our first attempt doesn't satisfy that requirement. So we append a value to that string and we hash it again. We're still not anywhere close to that goal, so this is literally hashing the string A1. So we increment the appended value and we try again. Still nothing. I think you can probably see where this is going. That ever-changing value is known as a nonce, and we keep changing it until we get a digest that meets our criteria. Don't worry, I'm not going to make you sit through slide after slide of hashes. I've already done that and found that for a value of A, the first nonce that results in a digest starting with 5 zeros is 862,183. That only took a second or so to find that value on this laptop, literally by brute force, starting at 1 and counting up, hashing every time and comparing the output to check whether it starts with 5 zeros. So in a real-life blockchain, the number of zeros that the hash must begin with is known as the difficulty, and it's going to be a lot higher than finding 5 zeros. We can implement this proof of work algorithm in a method on our block class. So we want to find a nonce for a given difficulty. And given that difficulty, we know that we want to find a hash with a certain number of zeros. So we're creating a string of that given number of zeros. And then we can loop. So while the hash does not start with that string of zeros, we increment the nonce and we calculate the hash again. So that means we need a nonce property on our block instances. We can start at 0. And we can include that value in our hash. We can now also update our create block implementation, and we can use that to actually find the nonce before we add the block to the chain. And we'll set up a default difficulty level. And we'll start at 4 because that allows us to find them very, very rapidly for the purposes of demos. So with that done, we have a fully functional blockchain, but we don't yet have a network. If I restart this server here, and I also quickly update the createGenesis block method to ensure we find the nonce there too, we can now see that the hash created for the Genesis block begins with 4 zeros. Sorry. Just as we've asked for, we've set the difficulty to 4, and we then, on startup of the node, we loop over again and again until we find a value that matches, well, a value that allows us to match that set of zeros. So I am just quickly going to jump to the correct point. Sorry. Cool, so we don't yet have a network. Most blockchains, Bitcoin included, use some form of peer-to-peer communication. Anyone can download and run a copy of the blockchain client, called a node. And our client currently creates a new chain every time it starts, which doesn't make it very useful. So the first thing we would consider adding is a mechanism by which nodes can find the current version of the chain when they start up. So this is quite an important concept. Any node in the network can broadcast a new block, but if 2 nodes happen to do so at almost exactly the same time, which block actually gets used? And the answer comes via consensus between a majority of nodes. If most nodes receive one of those blocks, they'll begin the process of adding subsequent blocks after that one, and they'll end up with a longer chain. So whoever holds the longest chain is deemed to hold the latest version, and peers need a way to communicate amongst each other and effectively find the longest chain. We also, as I just mentioned, need a way to send any blocks we create to the network. And conversely, a way to handle the receipt of those blocks. So our node already has the capability to communicate with peers, so we can just think about the actual logic here. So in our node, we can start with, let's start with a function to handle the receipt of blocks from the network. And we'll receive that from a peer, and it will have a packet of data. This is already configured via our peer-to-peer messaging system. So we'll say when we receive a block message, we call our handle receive block function. And in there, we can instantiate a new block with the given data that's been transmitted over the network. We can validate that block in its own right. So that means we're checking that its own hash is valid. We can validate the block in the context of our chain, which is checking whether or not that block directly follows the latest block that we hold. And if it does, we can simply append our new block to the chain. You might have noticed I did a git checkout to jump ahead, and that's added in a couple of methods just to save us having to go through mundane functions like appending to an array right now. So if the block's valid, and it's valid in the context of our chain, which is to say it directly follows the previous block that we hold, that's all good. We just update our chain with that block. However, if it doesn't directly follow, so perhaps my node has been shut down for a while, I haven't received a whole load of blocks that other nodes have all worked on together, it won't directly follow, and we won't be able to just directly append it because the previous hash will be wrong and the index will be wrong. So in those cases, as I mentioned a minute ago, we would need to find the longest chain from the network. So in that case, we broadcast a message to the network saying, we want the longest chain. If we add another function to actually handle that, we can then directly respond to the peer. So this message, that get blockchain message, will be received by all the peers in the network. And we can respond, each node will respond directly to that peer with its own message. So blockchain in response to get blockchain. And it can include our copy of the chain. And the final one we'll need is a way to handle that message itself. So when a node asks for the blockchain from its peers, it will receive a blockchain message with that data. And in that case, we can create a new blockchain instance from the data we've received. And we can check to see if the latest block in the received chain is of a higher index than the latest block in our chain. And if so, we've found a longer chain than ours, and we can just wholesale replace our chain with the chain we've received. If not, we can just ignore that message entirely because we already hold a longer chain. We don't have any interest in shorter chains. So we literally just drop that completely. So with that set up, we just need to call those functions, and I can cheat slightly here by jumping to a bit of a state where we actually already have that set up. Along with various bits of output, so we're now logging a few more things. we can now start a couple of instances of our node. So we've now got 2 instances running on a couple of ports. I can't actually see that port on my screen in front of me. So if we now send a message to this second node, we'll send a message to create a block on that second node. Oh no. Like I said, what can ever go wrong with live coding in a conference talk? It looks like chain get latest block isn't a function, so that was just a helper function to return the latest block in the chain. So we'll try that again. To the second node, in the middle on the right, we'll post a new transaction to create a new block. And we can see that this node has received that message and it's creating a new block. Zoom in a bit on this pane. This node then received that block. The new block is valid in its own right, but the new block was invalid for the current chain as held by that node, because when each node started up, each created its own chain with its own Genesis block. Our second chain then extended, added a new block in, which won't match the digest of the Genesis block in the other node. So that node has then requested the full chain. It's broadcast a message saying, my chain is invalid. Can I have the current latest version, please? It's then received that chain from its peer. And the received chain containing the second block, so length of 2 compared to a length of 1, and it was able to replace that chain with its own copy, well, with the new copy. So if we now create yet another block on the second node, no. Those little helper methods that I said we'd avoid to not bore you all, turns out we actually needed them. So hopefully this will work. So that was creating that first block again. And creating another block on the second node. So creating a new block, it then broadcasts that block to the network. The first node, has received it. The block is valid in its own right. And this time, because we requested the full chain from the network and this node hasn't created any of its own blocks in the time between, that block is valid in the context of the chain, and it's able to just append it directly. So if we were to then request the chain from either node, we should see there's 3 blocks. They all follow on from each other. so it's quite hard to read that massive mess of JSON there. But there are 3 blocks. Each node has synced between themselves, and they both share a copy of that same longest chain. So that's about all we have time for. But if you'd like some ideas for taking this further, there's a few things you could look into. As I mentioned earlier, in general, you wouldn't only want one single transaction in a block. In the Bitcoin network originally, blocks contain groups of transactions up to a limit of 1 megabyte worth of data. Another one from the Bitcoin network: as the network grows and more nodes are contributing to finding a valid nonce for the next block, you could consider dynamically adjusting the difficulty level, the number of zeros to find for the hash. And Bitcoin does that to ensure that blocks are found at fairly uniform intervals. And in Bitcoin, that's intended to be about every 10 minutes. And finally, to turn what we built into something vaguely useful, we'd have to consider some form of addresses by which we can actually identify other nodes in the network or other users to actually send them, well, to create transactions referencing those people, those users, rather than just hard-coded dummy identifiers like Alice that we used as an example there. So a great next step would be to look into how Bitcoin uses the concept of public and private keys for addresses to achieve that. Thank you very much, everyone. Any questions? I don't know if we have time. We only have a couple of minutes. No questions. Great. Thank you very much.